In this video, I'll introduce Lhopitals Rule as a method of finding limits of quotients. Here are the main points to be addressed in the video. Lhopitals Rule can be used when a ratio f of x over g of x has a limiting value of either 0 over 0 or infinity over infinity. Lhopitals Rule can be applied more than once if applying Lhopitals Rule results in a limit which is again of the form 0 over 0 or infinite over infinite. Sometimes limits can be rewritten to be form of 0 over 0 or infinity over infinity. Here's a limit as theta goes to pi over 2 of cosine theta divided by theta minus pi over 2. Pause the video and try to evaluate this limit. Were you able to find the numerical value for this limit? You might have noticed a few things. First, the denominator approaches 0 when theta approaches pi over 2. Also, the numerator approaches 0 when theta approaches pi over 2. Taken together, this limit is an example of what is called a type 0 over 0 indeterminate form, because both the numerator and the denominator approaches 0. There are two typical methods for computing the value of this limit. One option is to approximate by evaluating the function at angles successively closer to pi over 2. This method produces estimates, which may be very good, but it may take a lot of computation and sometimes these estimates are inaccurate. The alternative is a formulating method called Lhopitals Rule, which I'll describe in detail. You use Lhopitals Rule whenever you have a limit of a quotient, that is, when you're dividing one function by another, and quotient appears to approach 0 over 0 or infinity over infinity. Then, the limit of quotient is equal to the limit of quotient of derivative of the numerator divided by the derivative of the denominator, provided that both f and g are differentiable and derivative of g is not equal to 0. So let's think about how we can use Lhopitals Rule to evaluate this limit. First, both cosine theta and theta minus pi over 2 are differentiable, so we should be able to apply the rule. We already established that this limit is indeterminate type 0 over 0. We'll write LH over the equal sign to remind us that we'll use Lhopitals Rule in this next step. So the limit of this quotient is equal to the limit of new quotient where, according to the rule, we use the derivative of the original numerator and the denominator. So if f of theta is cosine of theta and g of theta is theta minus pi over 2, then we'll take the derivative of f, which is negative sine of theta, and derivative of g, since theta is a variable and pi over 2 is a constant, this derivative is just 1. Since negative sine is continuous at theta equals pi over 2, we can now evaluate negative sine theta at theta equals pi over 2, and this equals to negative 1. So, we have just used Lhopitals Rule to evaluate this limit. Let's look at another example. Here's a limit as x goes to infinity of e to the 5x power over x to the second power. Now, if we look at the numerator, this gets larger without bound as x goes to infinity. Similarly, if we look at the denominator, this gets larger without bound as x goes to infinity. So this limit is indeterminate type of infinity over infinity. And both the numerator and denominator are differentiable. One way this is different from previous example is that we have x going to infinity rather than a number. Technically, that is not what is currently written for Lhopitals Rule, but the rule still works even if x approaches infinity or negative infinity. So now that we established that we have indeterminate form and numerator and denominator are differentiable, we'll apply the Lhopitals Rule, which says we take the derivative of the numerator and the denominator. For numerator, we need to use the chain rule and we get the derivative of 5 times e to the x. e to the 5x. For the denominator, the derivative is 2x. Now, if we take a look at this limit, we can see that numerator gets larger and larger without bound as x goes to infinity. And the denominator also goes to infinity as x goes to infinity. So this new limit is also of indeterminate type, infinity over infinity. And we'll need to apply the Lhopitals rule a second time on this problem. Again, we'll need to use a chain rule for the numerator to get 25 e to the 5x, and derivative of denominator is 2. This time, the numerator goes to infinity as x gets larger because e to the 5x will continue to grow without bound, but the denominator is always equal to 2, no matter how large x may be. So this is not an indeterminate form, and the limit must be infinite because the numerator is growing without bound while the denominator is constant. Let's look at another example. Here's a limit as x goes to 0 from right of x, 0 from right side, of x times natural log of x. If you just look at x, this goes to 0. And the natural log of x goes to infinity as x goes to 0. So this doesn't initially look like an indeterminate form, but we can rewrite this limit as natural log of x divided by 1 over x. And now if you look at the numerator, this goes to infinity when x goes to 0. And the denominator goes to infinity as x goes to 0. So the limit is indeterminate type, infinity over infinity. Since both numerator and denominator are differentiable, we'll be able to use the Lhopitals rule. The derivative of numerator is 1 over x, and the derivative of denominator is negative 1 over x squared. This looks a bit complicated at first, but if you multiply the numerator and denominator by reciprocal of the denominator, this simplifies to just the limit as x goes to 0 from right side of negative x. And this limit is equal to 0. Now, we've gone through 3 examples how to use the rule. Let's think about why this rule works. To this, let's look at the first example again. There are some formal ways to prove that Lhopitals rule works, but I'll sketch out a basic idea here. Here is a graph of cosine theta in green and theta minus pi over 2 in purple. If we look at the limit as theta gets close to the pi over 2, then we're essentially zooming in to look at how functions behave at this value of theta. When we do this, the functions appear linear. So we can replace cosine theta with a line that is tangent to it at pi over 2. This equation of this line is a slope. That is derivative of cosine times theta minus pi over 2. We can also replace theta minus pi over 2 with a line that is tangent to it at pi over 2. This equation of this line is a derivative times theta minus pi over 2. And now we can replace numerator and denominator in this limit with these approximations. The common terms in numerator and denominator cancels, leaving us with the Lhopitals rule.